All right, topic 9.4, this is all about resolution or resolving images. So we have the first, this is the Rayleigh equation for resolution. Theta equals 1.22 lambda over b, where theta is the minimum angular separation between two sources of light. 1.22 is a proportionality constant for circular apertures, and the size of the aperture, or the diameter, is given by b. And then we have the resolvence equation, how powerful a diffraction grating is at resolving. So R equals lambda, where lambda is an average of wavelengths, divided by delta lambda, where that delta lambda is the difference between those two wavelengths, which is also equal to m, the diffraction order, times n, the number of diffraction gratings illuminated by the beam of light. If you've ever taken a long drive out through a stretch of desert, you may have seen something like this. Headlights from far away on oncoming cars will look like one. As the car gets closer and closer to you, you will see that there are in fact two distinct headlights. So two distant objects that are close together will look like one object if they are far enough away. So this animation shows that phenomenon quite clearly. Okay, two sources are just resolved using an aperture. If the following is true, please write this down. The first minimum of the diffraction pattern of one of the sources falls on the central maximum of the diffraction pattern of the other source. This is known as Rayleigh's criterion, and it might be easy to see if you do a little sketch. We have the diffraction pattern for one. The central maximum of this diffraction pattern for one source falls on the first minimum of the diffraction pattern of another source. So when these line up, Rayleigh's criterion has been met. So we have two equations for the minimum angular separation for having just resolved two sources of light. First is for square apertures, theta in radians equals lambda over b, and then we have the criterion equation for circular apertures, theta equals 1.22 lambda over b. So on this slide I have different examples of diffraction patterns overlapping, and I want you to tell me, looking at choices A, B, C, D, or E, which of the following are not resolved. Okay, and if you chose choices A and B, that is correct. These are not resolved. Okay, so looking at the remaining diffraction patterns, please tell me which of the following are just resolved. Okay, so in this case, there's only one that is just resolved, and that would be choice C. So here is a comparison of the intensity of light and the resolution for two light sources incident on a circular aperture. Please record these diagrams, the intensity, and the appearance of the beams. It will be helpful later on. So here we have an illustration of an eye, and let's discuss briefly how the eye resolves images. So imagine I have a beam of light, or some light source, and the beam is going to travel through the iris. The iris is a circular aperture. The beam passes through the iris, through the lens, and forms a diffraction pattern on the back of the retina, because that's what waves do when they pass through a narrow opening. Then we have a second source of light. Same thing, there is a second diffraction pattern formed on the retina. The eye is able to make out these, or to resolve the image when this angle in here, the minimum angle needed to resolve, matches the angular separation between the images. So when these two angles are equal, theta equals theta, you get resolution of the image. So you will need to know how the number of slits changes the intensity pattern. So as we add more slits, the intensity of the primary maxima increases, and the slits become narrower. So if we think of a diffraction grating as being a screen with hundreds of slits, we can imagine that the widths of the primary maxima are very small indeed. And using the Rayleigh criterion on these primary maxima, we see that the resolution for a grating will be proportional to the number of lines. Please pardon the spelling error. This is R-A-Y-L-E-I-G-H. Okay, so we have this equation for the resolvance R of a diffraction grating is defined then as the ratio of the average of the two wavelengths of light being resolved to their difference in wavelength. Thus, R equals lambda over the difference in lambda. This is the resolvance of a diffraction grating. Resolvance is essentially a measure of how well a diffraction grating can separate two wavelengths. As previously stated, grating resolution is proportional to n, the total lines illuminated by the incident beam of light. So look at the diffraction pattern for white light on the right-hand side. There's more spreading out of the pattern for higher orders. There is a natural separation of wavelengths that increases with order. The central maxima where you'd see the white light is m equals 0, and then you have first order on either side, second order on either side, third order on either side. So without proof, resolvance R for each order of diffraction m is given by R equals n times n. So modern diffraction gratings use a reflective surface with all of these edges cut in, machined into the surface, and then very precise calculations can be made by the path difference of the beams of light as they reflect and back onto a surface or photosensors. So the diffraction gratings we use in class are quite different than what people use analytical techniques in universities and other institutions. So just take a look at these, the progression of technology with the wavelengths of light and the apertures on a CD. So the original CD stored about 700 megabytes. It used around 730 nanometers of wavelength light, and the apertures were larger. The DVD, single layer, 4.7 gigabytes of storage space. If you could use both layers of the CD, 8.5 gigabytes of storage space. And notice the little holes inside are smaller, corresponding to the smaller wavelength of light, 650 nanometers. And now we have Blu-ray discs. This emits blue frequencies at 405 nanometers, and notice how small the apertures are because they're on the same order of magnitude as, they're some multiple of the wavelength, so smaller aperture. And now you have 25 gigabytes of space available for one layer, 50 gigabytes of space for another layer. So just the progression of technology over time is really baffling. Okay, so topic 9.4, this is the first practice problem. I just wanted to discuss this with you, how to solve this problem. Headlights of a car emit light of wavelength 400 nanometers and are separated by 1.2 meters. The headlights are viewed by an observer whose eye has an aperture of 4 millimeters. The observer can just distinguish the headlights as separate images. What is the distance between the observer and the headlights? So to quickly solve this problem without a calculator, because remember, multiple choice questions on the exam, you won't have a calculator. You need to relate the small angle approximation for the two sources of light with the aperture of the person's eye. And so these two sources of light separated by this distance of 1.2 meters. The light travels like so into the person's eye. So imagine these two purple lines I've drawn are the eye. And then this light diffracts out, forming an image on the back of this person's retina. So the angle, the angular separation between here, this theta, whoops, what happened to my red line, should equal the angular separation here. Theta should equal theta for a small angle approximation. So we are looking for this distance, I'll call this capital D, and we have the equation for diffraction through a small aperture, circular aperture. Theta equals 1.22 lambda over b. And in this case, my theta should also equal 1.2 divided by the distance, opposite over opposite side to the angle. This 1.2 is opposite, and the adjacent is d. So theta also equals 1.2 over d. I'm going to ignore the fact that this is actually the double angle. Both of these thetas really are the double angle. So the 2's would cancel anyway. So 1.2 over D equals 1.22 lambda over B. You won't get a calculator, so you will approximate 1.2 is approximately equal to 1.2, so that will cancel, and then you should be able to solve for your unknown D.